So here's going to be our first example for kinematics. This is 1D motion. The problem I chose picks x direction and y direction, horizontal and vertical direction, and we're combining the two. So you can see the problem. A ball falls off a bridge 45 meters above a river. The ball falls into a boat which moves with a constant velocity. The boat started initially 12 meters from the bridge. When the ball fell, we want to find the speed of the boat. First thing I suggest, if you're confused, always draw a sketch. So here I have the boat, I've got my cliff or my bridge, there's the ball, and my given information. Other thing you may want to add into that is, if you'd like, the acceleration we know is 9.8 meters per second squared, and that's straight down. Next thing I know, and I mentioned this in class, one of the more important things, you need to define an axis for your problem. Here you have an axis. I'm defining down as a positive direction, and I'm defining to the right as a positive direction. So as you can see, my boat is traveling positive and the ball is traveling in a positive direction. I then listed my given information. We know from the problem our initial velocity in the y direction is 0. I know it's falling because of the acceleration due to gravity, and I know the height of the bridge. The boat, since the boat is going at a constant velocity, I know the acceleration is 0. Because the acceleration is 0, that means my initial and my final velocity have to be the same. Only other given information is the boat going 12 meters. Ideally, we need to find time. We know time vertically, we know time horizontally are the same thing. So if I find the time in one spot, I know the time in the other spot, I can solve everything I need to know for the problem. So I have the most information in my y or my vertical. So the first step I'm doing is solving for y. I'm using my kinematic equation. Y minus y naught equals v naught t plus 1 half at squared. We know my initial velocity starts out at rest when the ball falls, so it goes away. Rearrange the equation, solve for time. You have two options here. You can plug in and actually get a number for time. I don't see a reason to do that. This is my general solution. This will always work for the problem. I'm going to use this time in my horizontal direction. I'm choosing the kinematic equation again that limits the things that I know. If I know my initial velocity, again, I know either one of those, it doesn't matter. Here I cancel out my acceleration. I know my acceleration in the horizontal direction is 0. Simplifying my equation, v naught equals x minus x naught divided by t. I just solved for t. Like I said, I solved it in terms of variables. Knowing that number is meaningless. My general solution, combining all of my terms in the x direction, my horizontal component, is the x position divided by the time. Plug in chug, you should get 3.95 or 4 meters per second. Okay, for my second example, here we have just some calculus with some kinematics. The position of a particle is moving in the x-axis is dependent on time by this equation. They tell us that x is in meters and t is in seconds. The things that we're looking for, very first, I want to find the constants, I want to find the units for C and for B. Then, given actual numbers for C and B, I want to find the distance to reach its maximum position. I want to know what the distance and the displacement is at times t equals 0 through t equals 4. And then we're looking for the velocity with respect to time, and the acceleration with respect to time at time equals 1, 2, 3, and 4 seconds. So the first thing I do here is we're trying to find our constants. This is something that's dimension analysis. It is something that's very powerful as we go through physics. Often you can check your answer just by checking the units, which is dimension analysis. So given our equation, ct squared minus bt cubed, things that I know x was given in meters. I know time is given in seconds, so I have seconds squared and seconds cubed. Simply looking at my unknown values, I know c has to be meters per second squared, so my seconds squared cancel out, I'm left with meters. I know b should be meters per second cubed. So my seconds cubed and seconds cubed canceled. I'm left with meters, meters, and meters. So I know that b, which is this variable, is meters per second cubed. And I know that c, which is the first variable, has to be in meters per second squared. From there, we want to find the maximum position of this particle. We know that a maximum position is when the velocity is equal to 0. So given my equation with respect to time, my position equation with respect to time, I'm going to take my first derivative. I know velocity is the derivative of position. So I take the derivative, 2ct minus 3bt squared. Plugging what I know. Notice I'm bringing my units down, so I know my units are going to work and they're going to cancel. All I'm doing here now is plugging in 2 times 3. I'm looking for t and for t. Once I have my equation, set the whole thing equal to 0. When I set the whole thing equal to 0, I'm simplifying here, skipping a step. I can factor out a 6t, and then I have 6t times 1 minus t equals 0. From there, I know the roots of my equation are 1 second and 0 seconds. Another method you can do here is once I had this equation, I can make a graph and find the roots that way. Moving up to the maximum positions, now I'm going to plug that in. I know my time has to be 1 and 0. Those are my roots. That means my maximum position is either at x equals 0 or x equals 1 second. Here I know when I sub in my time in my position equation that at x equals 0, I have a distance of 0 meters. At x equals 1, I have a distance of 1 meter. Therefore, my maximum position is at 1 second is x equals 1 meter. Next thing I wanted to do is find the distance at t equals 0 to 4 seconds. So what I did here is I chose times, 0, 1, 2, 3, and 4 seconds. That makes things easy to find the position at all of those places. And I started at 0. I went to 1, -4, -27, -80 meters. So my distance goes from 0 to 1, that's 1 unit. 1 back to 0 is 2 units. Then it keeps going all the way to -80 meters. So my total distance, 82 meters. My displacement, on the other hand, is by definition how far I've gone from start to finish. It is x minus x naught. I started at 0, doesn't matter where I went. I ended at -80. My displacement has to be 80 meters. Moving on to the velocity. Well, I already have a velocity equation. We derived that earlier on as 2ct minus 3bt squared. All I'm doing here is plugging in 1, 2, 3, and 4 seconds into my velocity equation with the given constants of 3 meters per second squared and 2 meters per second cubed. So plugging those numbers in, I have velocity at 1, 2, 3, and 4 seconds of 0, -12, -36, -72 meters per second squared, respectively. The very last step, we're looking for the acceleration. Just like we took here, we know velocity is the first derivative of position. Well, now here I know acceleration is my first derivative of velocity. So I take my velocity equation, take the derivative, dv dt, with respect to t. I know my derivative 2ct is just 2c, minus my derivative 3bt squared is 6bt. From here, I'm going to plug my constants back in. I'm going to plug my times, 0, 1, 2, 3, and 4. It started out with a positive acceleration, which makes sense because I was going from 0 to 1. Then it slowed down, stopped, and came back in the opposite direction. -6, -18, -30, -42 meters per second squared. Okay, last up we have the opposite of derivatives or antiderivatives. So I was given an equation, 3t in the I direction plus 4t in the j direction. So this is calculus in more than one dimension, or the xy plane. They told me that the acceleration was in meters per second squared and t is in seconds. Then they gave us some extra information. This becomes important information. They gave me unit vector r at time equals 0 and unit vector v at time equals 0 in my I and j direction. What I wanted to find is the position at t equals 4 seconds in vector notation, as well as the angle the position vector makes with respect to the positive x-axis. Lots of things difficult to start. The only thing I know is the acceleration equation. So that's my only equation with respect to time, so I need to utilize it. Things that we need to know. We need to remember calculus. If I have an acceleration with respect to time, that means I can derive a velocity equation and a position equation. We know that velocity is the first derivative of position. We know acceleration is the first derivative of velocity, so it goes the other way as well. I can take an antiderivative of acceleration with respect to time to get velocity, I can take two antiderivatives or one antiderivative of velocity to get my position equation. So that's what we're doing first. I know my change in velocity with respect to time, that's just my little trick here, is equal to 3ti plus 4tj. This is my another form, my acceleration. If I take the integral of both sides, so what I'm going to do is I'm going to integrate both sides. My notation is not perfect for calculus. My dt goes over there because I'm taking the antiderivative with respect to time. When I take my antiderivative of velocity of dv, I get v with respect to time. Here, my antiderivative of my expression, 3/2 t squared in the I hat plus 2t squared in the j hat plus c. That c is important. It's our integration constant. I need to know what c is. Luckily, they gave me these vectors. I know my velocity vector at time equals 0 in I and j notation. So I'm going to plug that in and combine. I know that at v equals 0, 5 meters per second in the I hat plus 2 meters per second in the j hat is equal to 3/2 t squared when t equals 0 in the I hat plus 2t squared when t equals 0 in the j hat plus c. Here I can combine, I can solve for c, 5i plus 2j in my unit is meters per second. Combine all of that back into my general equation for any v of t is my antiderivative, 3/2 t squared plus 5. That was my I hat here, plus 2t squared plus 2 in my j hat. They wanted to know the velocity at 4 seconds. Plug in 4 for t, plug in 4 for t. I get 29i plus 34j meters per second. To find my position, we're going through the exact same process. I'm going to take my antiderivative of my velocity equation. Here I have dx as the antiderivative of all that stuff that I know with respect to time. That was my general form velocity equation. I just separated it back out, so I had my t's and my non-t's. When I take the antiderivative with respect to t squared, I get t cubed. Both sides end up divided by 3. That simplifies to 1/2. That goes to 2/3. Here, 5 and 2, I don't have a constant, so I'm taking an antiderivative. So I have to have a 5t and a 2t here. And again, I have, you can't see me on camera, I have an integration constant of c. Exact same process now. I'm going to solve for c because I know position vector at t equals 0 is 20 meters I plus 40 meters in the j hat. Combine those exactly as I did before. We're going to set those equations equal to each other. We're going to solve for my integration constant. Integration constant is 20i plus 40j. Put everything together. I get a general expression, 72i plus 90.7j meters. Last thing I needed to do was figure out its angle. I'm sorry, this was at t equals 4 seconds. Last thing I need to do is figure out my angle. Well, I know position vector r at t equals 4 seconds is 72i plus 90j. 72, 90, I know my position vector is here. Take the inverse tan of 90.7, which is my, did I do that right? Yes, my y direction, my 72 in the x direction. I should have an angle with respect to the x-axis of approximately 51 degrees.